Now let's actually do the computation. There's a reason why I took some lengths to explain what the right side does. So I explained that when you do represent the function that way, you end up with a function whose values here are actually 0, 0, 0. The thing is, if I had the dots placed here, then that's no longer an odd function. But if I write like this is an odd function. See, previously it was not an odd function because f of 3 was 2, whereas f of negative 3 would be undefined, or maybe you can think of it as negative 2. But now there's 0 here and 0 there, so there's a symmetry. So this is an odd function. Whenever the right side goes up, the left side goes down, so there's a symmetry. And because it has this odd symmetry, we know that one of these are 0. Which one? Okay, so let me ask. Is this an even function or an odd function? Even, right? Is this an even function or odd function? Odd function. How about constants? Is that even or odd? It's even. If you have a straight horizontal line, you can fold it along the y-axis and it matches, so it's an even function, right? So if you had this function as an odd function, then all the even functions should be there because it should be a sum of odd functions. Only when you add odd functions together you get odd functions. You can't add an even function to an odd function and then expect it to be an even function. The only time that happens is when your even function is 0. If your 0 happens to be an even function and also an odd function, if you're adding 0 it doesn't change anything. But if you add any non-zero even functions, that's going to destroy the symmetry, and the resulting function won't be an odd function either, at all. So if we establish that the function is an odd function, then immediately these will be 0. We know that it has to be 0. Okay. Now, last time we argued for a0 and an to be 0 by using even and odd directly to the integral, right? And the argument goes like this. This is an even function. Fx is an odd function. Odd times even gives you an odd function. And if you integrate an odd function over a symmetric domain, what do you get? You get 0. All right? And therefore, ANs are all 0, and therefore we expect these to go away. But either way, I think this is quicker. Just say odd function, so even shouldn't be there. Okay, I think that's quicker. This discussion just saved us entire half of the calculation. We didn't have to do this at all because we knew that those are 0. So to solve this question, the only thing that we have to compute is just this. We just compute this, and after getting that, we just replace this bn by this number, and now you have the Fourier series of f of x. Okay, so that's what we're going to do. Okay. All right. So since we need some space, let me copy the formula with the an's deleted. So if I have f of x with only bn's, the formulas will be n from 1 through infinity of bn sine n pi over L x. And then the formula for Bn is right here. It's 1 over L. But what's our L for this case? We drew the graph. It's from 0 to L, right? So when you have a function defined in some interval, always it's from negative L to L. So you can read from this definition that it's L and negative L. So L value should be 3. And your integral should be from negative 3 to positive 3. Okay. And what's f of x? Well, we don't know f of x. So, I mean, it's complicated, so let's leave it as f of x. And sine of n pi over 3 x dx. That's what we have to compute. All right. Now the integral. This is odd or even? F is odd or even? Odd. Sine is odd or even? Odd. Odd times odd is? Even. So what can you do in that case? What's a good thing to do when you're integrating an even function?
You can do it multiply by 2.
You can put times 2, right? And take the half the interval, right? So instead of going from -3 to 3, you go from 0 to 3, and you double the integral value. Because even functions have this symmetry, and if you're integrating over a symmetric domain, you just have to integrate one side and double it. It covers the other part automatically. So that's a shortcut for dealing with even functions. Okay. So let's do it. Let's use that nice property. So this is what we have. Bn is now 2 over 3, 0 to 3, f of x sine n pi over 3 x dx. Right, where did this 2 come from? We're using the fact that this is even, so we double the integral at the cost of starting from 0 to 3, or rather than -3 to 3. Okay, so that's what we did. And already we can reap its benefits, because what's f of x from 0 to 3? 2. This is 2. So now we can just replace this f of x by 2. How wonderful is that? Now, how would we do this if we could do that trick?
Wait, why didn't you replace it with 2?
Oh, because in this interval from 0 to 3,
Oh, it's always 2, yeah.
the function is always 2, so I just replace it by 2. Now, if we did not use that trick, then the only other way to calculate this integral will be actually to split this integral into 2 intervals. So from integral from -3 to 0 would be using the value of -2, and integral from 0 to 3 will be using the value of 2. So you'll have to compute not just one integral, but 2 integrals. And that's much longer. You don't want to do that. This is much better. Okay? So we did this. And 2 is just a constant multiple, so we pull it out. It would be 4/3, and we just have to integrate this one. You still have a question? What's your question?
Just for the f of x to 2.
Yeah, see, in this integral, you're trying to use the value of f of x on this interval, 0 to 3, right?
Okay, so you just...
And then you look at this function on 0 to 3, f always takes the value of 2. So there we go. Okay, and then if you integrate sine, it gives you negative cosine. And then we also learned that whatever that's in front of this x, the reciprocal of that should be in front. So it's 3 over n pi. It's all multiplication. And then n pi over 3 x, and you still have to plug in the endpoints 3 and 0. That's the integral. I see that 3 and 3 cancels. That's nice. I like canceling, so you can cancel early. Right. Let's pull the -4 over n pi outside, so that we don't want to. We can just forget about that. All we need to do is cosine of n pi over 3x, evaluate it and subtract it at 3 and 0. Okay? That's what we have to do. When you plug in 3, what do you get? Cosine of? Okay, n pi over 3 times 3, so 3 cancels, so you get cosine n pi. When you plug in 0, what do you get? You get cosine of 0. Which is -4 over n pi, which is, what's cosine n pi? Yeah, I told you to memorize this as a formula, right? Cosine n pi is -1 to the nth power. Let's not forget this. We will use this frequently. So this is -1 to the nth power. What's cosine of 0? Huh? Cosine 0 is 1, right? Yeah. So that's it. That's your Bn. Therefore, what's the Fourier series of the given function? Fourier series of the given function is sigma n from 1 through infinity of -4 over n pi, -1 to the nth power minus 1, and then cosine n pi over 3. No, not cosine, I'm sorry. Sine, right? Sine n pi over 3. Yes. So all I did was, after finding the value of Bn, I just replaced this Bn by what we found. And that's the final answer. And I guess the fun part will be to actually draw the graph of that function and verifying that it is almost same as the graph of this one for n pretty large. But since I showed you such graphs in my slides several times, you probably already know what that means, okay?